Ever wondered why huge ships don't sink but a small pebble does? Welcome to the fascinating world of buoyancy. This invisible force is a fundamental principle that governs the behavior of objects in fluid, be it a gargantuan cruise liner or a diminutive marble. It's a principle that finds its roots in the work of the ancient Greek mathematician Archimedes. A principle that's often overlooked but is omnipresent in our lives. Now, let's delve deeper into this magical phenomenon. So, what's this principle all about? In simple terms, buoyancy is the force exerted on an object submerged in a fluid. But let's break it down a bit more. When an object is immersed in fluid, be it water, oil, or even air, it experiences an upward force. This force is what we call buoyancy. Now, the magnitude of this buoyant force depends on a couple of factors. First, it's dependent on the volume of the fluid that the object displaces. The more fluid displaced, the stronger the buoyant force. Second, it's influenced by the density of the fluid. The denser the fluid, the greater the buoyant force. And finally, it is determined by the gravitational pull. But here's the kicker: an object will float if the buoyant force is greater than its weight, and it will sink if its weight is greater. In other words, it's all about balance, the balance between weight and buoyancy. But who discovered this principle? Meet Archimedes, the ancient Greek mathematician. Born in the city of Syracuse in the 3rd century BCE, Archimedes is celebrated for his remarkable contributions to mathematics, physics, and engineering. Yet, it's his eureka moment that made him a household name. Legend has it Archimedes was tasked by the king to determine if a crown was pure gold or a mix of gold and silver. Puzzled, he pondered this problem until one day, while taking a bath, he observed the water level rise as he submerged himself. This observation sparked a realization: the volume of water displaced was equal to the volume of his body submerged in the water. This, my friends, led to the formulation of the buoyancy principle, which states that the upward force on an object submerged in a fluid is equal to the weight of the fluid displaced by that object. And that's how Archimedes' principle came to be. Now that we understand the principle, let's see it in action. Buoyancy isn't just a concept confined to textbooks and science labs. It's a fundamental force that shapes our everyday lives, even if we aren't always aware of it. Let's delve into some examples that illustrate how buoyancy comes into play in day-to-day situations. Imagine you're at a pool party, and you notice a beach ball floating on the water. What's keeping that ball afloat? You guessed it, buoyancy. The beach ball displaces a certain volume of water, and the upward force exerted by the water is equal to the weight of the water displaced. This principle of buoyancy is what keeps the beach ball happily bobbing on the surface. Now consider a ship sailing across the ocean. It's made of steel, and steel is denser than water, right? So why doesn't it sink? Again, buoyancy comes to the rescue. The ship has been designed in such a way that it displaces a large volume of water, which exerts an upward force equal to the weight of the water displaced. This force counteracts the weight of the ship, allowing it to float. But what happens when you drop a stone in the water? It sinks, doesn't it? That's because the stone, being denser than water, displaces only a small volume of water. The weight of the water displaced is less than the weight of the stone. So, the force of gravity pulling the stone down is stronger than the buoyant force pushing it up, causing the stone to sink. Then there's the case of a helium balloon. Have you ever wondered why a helium balloon floats in the air? Again, it's all thanks to buoyancy. The helium inside the balloon is lighter than the air it displaces. So the buoyant force exerted by the air is greater than the weight of the balloon, causing it to float upwards. These examples show how buoyancy is a part of our everyday lives. It's a simple principle with profound implications governing everything from the float of a beach ball to the flight of a helium balloon. How about we take a quick look at the mathematics involved in buoyancy? Diving into the depths of buoyancy isn't complete without understanding the math that powers it. The formula that governs buoyant force is the brainchild of our good friend, Archimedes. It's as simple as it is profound. Buoyant force equals the weight of the fluid displaced by an object. Let's break it down. First, there's the fluid. It could be water, air, or even a vat of molasses. The fluid has a certain density, which is its mass per unit volume. Then we have gravity, the force that keeps us grounded. It pulls everything downwards, including our object and the fluid around it. Next up, the object. It has a volume, and it's this volume that displaces an equivalent volume of fluid. So when you put it all together, you get the formula. Buoyant force equals the density of the fluid, times the volume of the object submerged, times the acceleration due to gravity. In mathematical terms, it's Fb equals Rho times V times G, where Fb is the buoyant force, Rho is the fluid density, V is the volume of the object submerged, and G is the acceleration due to gravity. And there you have it, the math behind buoyancy. So the next time you see something floating or sinking, you'll know exactly why. We've come a long way from wondering why ships don't sink to understanding the principle behind it. Let's quickly recap what we've covered today. First, we defined buoyancy, an upward force exerted by a fluid that opposes the weight of an immersed object. This is the principle that keeps our ships afloat and allows us to swim. Then, we delved into the life of Archimedes, the ancient Greek mathematician and inventor who first discovered this principle. His eureka moment in the bath is one of the most famous stories in the history of science. We saw buoyancy in action, with examples ranging from hot air balloons to submarines. Each example demonstrated how the principle of buoyancy is utilized in our daily lives. Finally, we delved into the math behind buoyancy, examining Archimedes' buoyancy formula. This formula, weight of the fluid displaced equals the buoyant force, is a cornerstone of fluid mechanics. Thank you for joining us on this journey into the world of buoyancy. Stay curious and keep exploring.